have a that requested I recorded lectures because they have conferences or trips that they have to make, and so I'm starting doing this again. Okay, but I hope the attendance is improving, or I just don't know how to count again, which is my inherited problem. But I'm working on it. All right. Like I said, we have one quiz that I posted yesterday. Okay, yeah, I think it's next week is the deadline, so you have 30 enough time to handle the quiz. Now about the exam, when is Halloween? Next week, this week? Next Sunday, right? So should we have exam next Thursday? No, too early, too soon. Elm Street comes in reality. Okay. All right. How about the first week of November or second week of November? Second week, right? Of course. One more week study. Okay. Let's tentatively make it on second week of November. Okay, tentatively. All right. And that may be a little bit late. We'll see, but I think it should be safe. The problem is that we'll get into a little bit content covering the final exam at the time we do the second exam, but I figure that should be fine. So you guys have more time to study for it. Okay. Now, I got a few students score lower than 60. And I still feel they're literally just one guy. I don't want to name names. If you're here, you know who you are, come talk to me after class. If you're not here, then no bother, right? I just make things a little bit simpler for me, okay? But that's what it is. And now for a lot of you guys on the borderline of 80s, 90s, right? The second exam is going to be your chance of salvation, all right? I think I've talked to you guys specifically, individually. With a little bit of push, you can make a solid A, okay, if you do well in the second and third exam, all right? Now, do you guys check your grades, the homework grade? Are these all updated, everything up to date? Okay, do this, right? Add up all your scores from your homework and quizzes. Take us at 25%, I believe, or 20% check the syllabus, okay? Calculate your current grade. I think if you're really at a solid A, then you're probably going to be fine if you can maintain your exam scores about 85 for the second and third simultaneously, okay? That means both of them. And if your grades is on the borderline of A's, like 75 or 85, you know, not quite there yet, you need to push a little bit. But if you have 60s, right, I think that's golden opportunity. If you work a little bit harder than that, I believe you can get a B, no problem. Okay, I'm a very nice professor. My grades in this course is always quite high. So don't ask me how I did it, but I think a lot of effort has come from you, not me, right? So you need to show me what you can do. Okay, so if I see anywhere, I mean, if your answer is anywhere close to the final correct answer, I'll give you credits. That's how easy I make it. Okay, so just work hard a little bit on it. Okay, now one more thing about the masks. I don't wear them just because I tend to forget. It doesn't mean I think it's not important, okay? And I think the virus is still spreading. I will try to wear it whenever I get a chance to pick up from my car. I don't want any peer pressure. What I mean by that, if you want to wear them or if you prefer to wear them, do wear them. And applaud several key people, you're wearing them, protect yourself. I like that idea, okay? So I don't want to feel any other way, okay? I'm just lazy, all right? I don't have any preferences. I might just pick up next lecture. Okay, so that's something I want to just say out here. Okay, now about what I was going to say about the final exam. I made the problem last night actually preemptively. I just like to make exams. Okay, I want to make sure I have 3 versions for the final exams because I didn't make it in the first exam. Okay, so I think I made 1 version last night and I'm going to make 2 more versions in the finals. All right, so there are going to be 4 to 5 problems actually, as I look at it. So really do well in the shear department, okay? I think I give very good grades, credits for the shear problem, okay? I think that's it, all right? Okay, any other questions about the grades so far? Any questions? If you're not happy about your grades, come to see me after class, okay? Right now, it's like mid-semester marks, so I just want to make sure everybody is on the same page, all right? Okay, oh, all right. Without further ado, let's talk about shear, shall we? Let's talk about shear, okay? And what we have learned so far about shear. Last time, we have gone over some of the theoretical equations, right? and talk about where shear force is going to coming from in terms of different stresses and crack, right? One thing we learned that shear always fail in terms of crack, and that in terms of diagonal crack. What is the angle for that diagonal crack? 45-degree angles. Why that is so important? Why is it? We use that for what? To determine what? Number of stirrups that able to be placed there in the diagonal crack. And how many stirrups I can have per a 45-degree angle crack. If I know the stirrup spacing S, how many, and the depth of the beam is D, how many stirrups I have for the crack? How many? How to calculate that? N equal to what? D over S. Is that right? So that's how many stirrups we have. And now there are two components of shear resistance contributed, one from concrete and the other from steel, right? And what is the shear resistance from concrete? What is it? Equation 2, start from 2, and then what? 2 lambda and square root of F prime C, then what? BWD. What is BW? The minimum width of the section. If I have a T-beam, that's the web width. If I have a rectangular beam, that's just a regular width, right? So that has to be remembered, okay? Now, we had a little table yesterday, right? And this is a table right here. I just want to quickly go over it. So column number 1 on the left, basically showing you that if half of the concrete resistance is sufficient to resist the shear, apply shear, we're going to use the minimum spacing. And those two equations are coming from the minimum spacing. That is FYTAV divided by 0.75 square root of prime C BW, or FYTAV divided by 50 BW. So what is FYT? What is FYT? FY, what is FY? Yield strength of the longitudinal bar, right? And what is FYT? Yield strength of what? Stirrups, right? So if the yield strength of stirrups exceeds 60 KSI per se 75 KSI, what do we do? What do we do? First, is that okay? Is that okay? Is that allowed? I mean, it's allowed, right? Any bar that I can pick up from job site is fine, right? But if the strengths exceed 60 KSI, when you do calculation, what do? You use 60 KSI. We have to cap it, okay? Cannot exceed that 60 KSI value, okay? All right? Just, follow me right now. Don't look at your notes, anything, right? Just recall what happened yesterday, right? Like watching the videos, right? TV episodes, right? What happened last time, right? My wife watched Downton Abbey, right? What happened last time? Matthew and Mary, right? What kind of story? Whatever, right? Now, think about it. For the stirrups, how many legs are there in the stirrup? 2, right? For regular stirrups, right? 2. And for number 3 size stirrups, what is AV? What is AV? 2 multiply 0.11 inch squared, so 0.22 inch squared, right? Thank you for the correction, by the way. Number 4 stirrups, what do I have? 0.2 multiply 2, 0.4 inch squared. Easier. There you go, right? That's it, simple, right? So that's what we have learned, the basics. Okay, so what about shear design? We use this column, right? So let's review this column. Column number 1 is saying that if half of my concrete resistance exceed the applied shear, and that is not on your phone, sir, not on your phone, sir. And what happens? We need to pick up the spacing that covers the minimum spacing, right? So I have 2 equations right here. I need to pick up one out of the 2. Quick question. Do I pick the bigger one or the smaller one? Smaller one. Smaller controls, right? So move up a ladder. I say if the concrete resistance covers the applied shear, right? But the half of it does not cover it, right? A little bit higher than the first column, goes to the second column. I pick out of this 24 inch, half of D, add these 2 fellow here, okay? And then if the shear, applied shear increase a bit more, a hair more, and I find myself in a situation that just the concrete itself cannot cover the applied shear force. I need to rely on the steel to provide additional resistance, right? But I need to do a check to make sure that the provided shear resistance from steel is smaller than 4 times the square root F prime CBWD. Okay, and when that happened, when all satisfied, I picked the 4 out of this 24 half D, and these two added 1 from the calculation. Okay, added 1 from the calculation. That is so-called required spacing. What is the equation for the required spacing anyway? The required spacing is right here. Okay, so that is AVFYTD multiplied VU minus V minus VC. That is required shear resistance from the steel. Right? So that is the added term to those 4 terms. So become 5 terms. All right. So keep going, right? Now we have that. And I say, what if my steel VS is greater than 4 times square root F prime CBWB? What happens? The rest of the 3 terms in the lower position of the column stay the same, but the first two terms changes by half, reduced by half. So it's no longer 24 inch, but 12 inch. It's no longer half of the depth, so a quarter of the depth. All right? Right? Now, last but not least, if my VS is greater than 8 times of F square root F prime CBWD, what happens? Increase the section size. So when we try to change the section size for flexure, which dimension we go for? Depth or width? For flexure, depth or width? Depth, right? For shear, which way to go? Either one, right? But we usually go with what? The width. Why is that? Because for T-beam and I-beam, increased width does not increase the occupation of area or space that is so precious for civil engineers. Okay. Nowadays, right? You heard this. What is the most important thing about real estate? What determines the price? Heard this before in the House of Cards, right? We watch the House of Cards. Location, 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 right? So everything we work with as civil engineers is about locations, about how big a piece of land the investor bought it, right? We have to constrain ourselves with the space that is allocated, available to us, right? So we don't want to occupy more space than we have to, okay? But we want to utilize efficiently, okay? So increase the width instead, right? Okay, get that. So, and last but not least, right, I forgot to mention this. If the yield strength greater than 60 KSI, take 60 KSI for the calculation, that's it, okay? And our life in terms of shear design pretty much was confined by this tiny table here. It's not too bad, isn't it? It's not too bad. Now, let's start showing an example, right? And then we show the example and where we have the critical section about D away from the support. And we draw the 45-degree angle always like this. That's how the crack happens. I will ask you guys to draw these cracks in the exam on the critical sections, right? So this is kind of like the Japanese animes, right? So you do this sign, right? You do this sign, right? You never do this sign, right? That's too awkward, right? You do this sign, right? Meaning 45-degree diagonal crack like this, okay? I don't want you to draw like that, right? Always like this, okay? We'll go through that later. But anyway, that's where we start. And we say now the concrete is 4 KSI, yield strength is 60 KSI, normal weight concrete, be careful. This is the best part. I always trick my students. Sometimes I say lightweight concrete at the end of it and don't tell you what does it mean. That means lambda equal to what? Lambda equal to 0.75 when it is lightweight, right? You're not smart, right? You're just okay, right? So you have to pay attention, all right? Now, we talked about last time, we had 12K, 24K, 54, 77, 120, and so on and so forth. So first thing we do is we find out applied shear, 12 kips, and we check whether half of my concrete resistance satisfy this or not. So it turns out I'm okay, right? So half of this resistance from concrete alone can take care of the applied shear, and we can pick bars. So for the sake of conveniences, I'm just going to pick number 3, and it gave me a 0.22 inch squares of a steel area. And I went down, find the maximum spacing has to be lesser of these 2 minimum requirements, and that gives me 22 inches. All right. And when I see 22 inches, I'm okay, right? I'm happy. Why is that? Because this number is smaller than what? 24. Okay. Even though, all right, this is practice. Even though when you do design, you can come up with some weird numbers. For this one, remember in this column, there's no constraint about 24 at all, right? For column number 1, right? You just need to provide minimum. But still, in practice, as a good civil engineer, I always maintain my spacing lower than 24 inches, just to be safe. Okay, call me paranoia, but this is what I do, right? Just make sure I'm on the safe side. Okay, so I think that's a good practice. Keep it below 24 inches. So then we jump up our shear to 24 kips, right? And then we say that, okay, apparently half of the concrete does not cut it. I need to have steel, right? No, not yet. Not yet. That just means my half of the concrete does not cut it, meaning I need to provide a little bit more reinforcement. Does not mean I have to calculate how much reinforcement I need to apply. Do you understand the difference? Right? Meaning I don't need to calculate, but I need to provide a little more than just minimum. So I go on with that idea, I say fine, but I check that steel is definitely smaller than that. So I have 24, totaling 1.5, that is depth divided by 2, then the previous 2 minimum spacing, then I pick 10 inches. Out of this 10.75, calculate from the depth divided by 2, and then I pick 10 because it's smaller than the calculated numbers. Then I'm left with a quiz, and today we'll continue, right? Then C. Okay. When we have VU, that is 54 kips, what happens, right? So now from previous calculation, I know that phi VC equal to a 24.5 kips, okay? And that pretty much tells me this shear itself does not work anymore because this one is definitely smaller than the 54 kip of shear force. All right, so immediately I say, well, you know what? Stirrups needed. No way you can get out this one, Bob. Just need to provide stirrups. And to be precise, I need to calculate it. So how do I calculate it? First, I need to calculate so-called the required shear resistance for steel, VS required. So how do I get that? That is basically VU divided by phi minus VC. Okay, so what is VU? 54 kips divided by 0.75 minus VC, that is 32.6 kip I previously calculated, and left me with 39.3 kips. Okay, so that is how much shear force I need from the steel. All right, at this point, should I start calculating my required spacing? Yes, I can do that, right? And that is AV FYT multiplied by depth D divided by a VS required. Okay, so bring the number in, and now I'm picking number 3 stirrup. So 0.22 inch squared, and FYT 60 KSI of yield strength, and 21.5 inch of depth, and divided by the required shear force, and I have 39.3 kips. Okay, and folks, unit, right? Inches squared, KSI, kips per inch squared, and inches and kips. So I'm fine. Unit are balanced. Now continue with this. I got my required spacing S required equal to a 7.26 inch. Okay, 7.26 inch. All right. So at this point, I calculate the spacing between stirrups needed based on my required shear force, but I don't know yet. Why am I saying that? Because I need to go back to my table, see where are we at. So now we're definitely not in category number 1 anymore, isn't it? We're not there, right? Because half of the concrete does not cover it. Are we in category number 2? No, definitely not, right? It's more than that. We need steel. Come on, Bob, wake up, right? Need steel. All right, well, I got you steel, right? Are we in number 3? Maybe because you arranged the problem like that, Bob, right? But I need to check. I need to check, right? So what is the criterion? What is difference between number 3 and number 4? Which one is the criterion? 4 square root from C, BWD, right? I need to check that. I need to check that. And just when I'm doing that, might as well take a look at this as well, right? Whether I need to change my section at all, right? So these are 2 criteria I need to check. So here I'm doing a check first. I say, all right, let's do a check. First thing I need to check, right, is to make sure that my VS required And that number is calculated 39.3 kips. And it is smaller than what? A times square root f prime c. I start from the bigger one, right? And that I can calculate it and tells me it's 130.6 kips. So I'm okay. Meaning I don't need to change my section. Happy with it. And then how about VS required? That is 39.3 kips again, whether it is smaller or greater than 4 times the square root of prime C BWD. And that essentially is 130.6 divided by 2, and I get this number 65.3 kips. And of course, it is again checked. It is again checked. So now I can say by the table, and this is my own table, so I'm just going to call it table star. Whether you like it or not, you can name yourself, right? So this is table spacing, right? Just call it that. And then I am here in my category number 3, right? So I know now my spacing has between S max equal to the least of, so remember those terms, 24 inches. D divided by 2, we know that is 10.75 inch. And the 2 small ones, FY, T, AV, D. Do I have a D or not? I can't remember. Let me see. I don't. That is 0.75. And bottom here, square root of prime C, BW, and that is 23.2 inch. And I have AV, FYT divided by a 50, BW, and I got 22 inches. And don't forget, we just calculated as required is a 7.26 inch. Now, out of the 5, which one governs? Which one is the control value? Which one? Should I go with, 23.2, 24? No, right? You're not dumb, right? I am the only one who's not smart here, right? Which one is the good one? 7.2. Okay, so you know that this one governs, because this is the smallest one. All right, so I am going to give spacing now, right? So I need to pick a spacing S that is smaller than this maximum spacing, which is 7.26 inch. So if you were the contractor, what is spacing you pick? I get a 7.
It's a 6.
Do I get a 6? Why go with 6? It's just easy, right? Hopefully. So I will go with 6 inches to make sure that is 7.26 satisfied. Okay. Is that over? Yeah, sure. It is over design, but is it safe? Yes, it is pretty safe. Okay. So that is the criteria I'm going with. All right. Now we're done with C, right? Quickly, I say, look, with this case, don't forget, I'm going to design and using number 3 stirrups at a spacing of 6 inch. So this is what you see in the blueprint. You don't see the calculations at all, right? Some poor, hard engineer worked all night long, red eyes and everything, right? 2 coffees later, you see this. Unfortunately, that's what it is, right? Number 3 at 6 inches. So you know that's how we're going to construct it. All right. At this point, we say, all right, much relieved. Shall we go to next level, right? Shall we use VU equal to 77 kips? Right? 77 kips. And you probably guessed it. At this point, we're probably going to category number 4 now, right? But just want to make sure that is the case. So 77 kips, that is greater than VVC, right? We calculate this, and that is 24.5 kips. What does it mean? Means I'm copying whatever you wrote down, Bob. I don't know. What does it mean? I'm writing this, but what I mean by this? I need to use steel, right? So simple, you got to use steel, right? Then I say, look, to use steel, right? I need to calculate my VS required. Okay, VS required. And that is VU minus divided by phi minus VC. And we calculated this before, and that turns out to be a 70. Well, we haven't calculated this one before, right? So sorry about that. 77 divided by 0.75 minus VC, that is 32.6. So I got a 70 kips of VS required. So now I'm at the junction here, right? Miller's cross, right? Which way to go? 2 checks. Again, 2 checks. Am I bold enough to change my section or not? So section size check. Okay, I start naming names, right? So VS required, that is 70 kips. So it is definitely smaller than 8 times FC prime C squared BWD. And that is, again, remember this, 130.6 kips we did before, right? So we're okay, meaning no need to increase my concrete section size. But should I do the halved spacing or not? Whether it's category 3 or category 4, I need to check it again. VS required, then it is 70 kips, and it is definitely greater than 4 times the square root of prime C BWD, and that is 65.3 kips. So by the table, we're going with category 4. What is category 4? That means, and I use red here to remind you that reduce spacing by half. So, Bob, what do you mean by reducing the spacing by half? That means my maximum spacing now is least of, and the bottom 3 stay the same. That is AVFYT 0.75 square root of prime C BW and AVFYT 50 BW, and even F required 7.26 inch stays. So this is 22 and this is 3.2, maybe reverse lay, can't remember now, but you get the idea, 22 inches. But now the only 2 number need to be halved, okay? Only 2 number need to be halved is what? Is, let me save this one, it's not 70.26. Let me save this one, okay? The only 2 number need to be halved is 24 inch divided by 2, that is 12 inch. And D divided by 4, that is 21.5 divided by 4. And I have a what? 5.3 inch. Ooh, that's awfully small. That's awfully small. But we're not done yet because the S required is different from the previous one. You had to recalculate it. It's AVFYT multiplied by D divided by VS required. And VS required has become a 70 kips. And AVFYT 0.22 inch squared multiplied by 60 KSI multiplied by 21.5 inch. And I got this number to be 4.1 inch. Now, you look through all these numbers, which one governs? Which one governs? 4.1 inch governs. So this one fellow is our friend. So now I say S better to be 4 inch and to be controlled by this 4.1 inch of spacing. So for me now we say design is number 3 at 4 inch. All right, not too bad, right? So we're happy, we're okay. All right, now naturally, let's bump up another level, right? Say, I want to see what happens, right? I want to bust my section. I want to fill it. I say, I want to increase the applied shear to be 128 kips, okay? And that gives me a VU, 128 kips, definitely larger than VVC, of course, needs steel. Steel needed, right? And I need to check my section size, right? Now, previously, I already know it's greater than VS required, right? What is VS required? VU divided by phi minus VC, and that is VU is what? 128. And please pull out your calculator because Lazy Bob did not calculate this number yesterday, okay? Can I get a check on this? What is this? Come on, help me out, right? Jerry Maguire, right? Help me, help you, right? Help me, help you, right? What is this number here, fellows? 138. 138. Do I get a second? All right, good deal. Now, I have my required shear force, right? Immediately, I know it is definitely larger than 4 times of square root F prime C BWD. So I know my spacing has to be halved, no problem. But the most important check is whether I need to increase my section or not. So VS required is 138 kips, and that is to compare greater, unfortunately, greater than 8 times square root F prime C BWD. And that number, ladies and gentlemen, is 130.6 kips. Okay, 130 kips, right? So we're in a dilemma here to change the section size. So I look at my section size, I say, well, originally I have a 2 footers, 24-inch in the height, and 16-inch in the width. Now I got to increase the section size, right? Increase size. So we said, Bob, you can go either way, right? You will not lose. And I think this is 12, not 12, 16. Okay, sorry about that. 112. Okay, but I prefer to change the width. So the question is, bless you, how much width do I change? What number you give here? Roll the dice. Russian roulette. Pick a number. 18, right? Why 18? How do you know? How do you know it's 18? So what is the judging criteria, right? What is the card count when you play blackjacks, right? What is the trick here? How do we know that? So we know that the concrete, right? Remember the concrete VC, right, is what? What is VC? Come on, remember the equation? 2 lambda is 1.0 for now. Square root of what? F prime C and what? BWD, isn't it? So that is, if I draw my shear resistance in concrete as VC, and I fix my concrete, fix my depths, and I want to plot a VC versus BW, the width, what kind of shape or what kind of function I'm seeing here? A straight line, isn't it? A linear relationship, isn't it? Right? So things become easier. Things become easier, right? So if I have my VS required, right? And divided by, well, I shouldn't say divided by. If I have right now VS required right here is at what? 138 kips. And I want to lower that to be below a 130 kips. But that is steel, isn't it? You say, Bob, that is steel. That is not concrete. What are you doing here, right? And that is 130.6 kips. I understand that. I know that. But although these are steel, okay, but maybe I can use this ratio to guide me. Okay, maybe I can use this ratio to guide me. That is, can you help me out? What is 138 divided by 130? What is this? Quickly, 1 point something, right? 1.06, right? So if I increase my section from 12-inch to 12 multiply 1.06, what I have here? 12.72, right? So if I just increase to about 13-inch, I should be okay roughly. Although I need to do some plus and minuses, right? Go back to plug in the VC and VS, everything, check my VU, right? Should be okay, isn't it? So I know that I just need to have a section bigger than 13 inches. So what is bigger than 13? 14, right? Of course, right? I use even number, 12, 14, 16, right? But on job site, usually they go by 4-inch increment with formworks. So what is above 12? 16, right? So you're right, 18 would work. But lazy Bob here will go 16, just making my life easier. All right, not complicated, isn't it? Pretty street smartness, right? street smartness, but you need to know this. You know this, right? Kind of get a proportion. And of course, this is not really correct images, okay? Don't show this to people, all right? Have this in your mind, don't show it to people, okay? You can check me, but it's just roughly linear relationship. That's it. That's what matters, okay? Not exactly one-to-one, but that's what it is. All right, so now I think we're probably gonna go with 16 inches and repeat the whole process, but I'm lazy, so I'm not gonna do that. So quiz number 10. Okay. I want you to try this, right? But this time we'll have a 16 inches and 24 inches, okay? And let me increase my bar. I want to use number 4 stirrups. Okay, number 4 stirrups. Okay, and give me the phi VN. Okay, and let me say number 4, and sorry, but let me just give you the whole information instead of confusing. Number 4 at 6-inch spacing. Okay, phi VN equal to what? And prime C 4 KSI, and yield strength of YT is 60 KSI. Okay, nothing else. Right? Shouldn't spend you more than 5 minutes on this, okay? Shouldn't spend more than 5 minutes on this, okay? Just need to find which one, the equation for it, right? Don't even have to judge the category, okay? Don't even have to judge the category, all right? Okay, all right, so that's it, quiz number 10. Just one more exercise, all right? Okay, so at this point, you're ready to go. Literally, I should be able to drop you on the job site, say, design for it. And for the building collapse, if I'm not stamping on them, fine, right? Question, yeah.
Is DS still 21.5?
Yes, sorry about that. Yeah, you're right. DS 21.5 inch. Thank you. Yep. Okay, but like I said, if I throw you right now to the job site, you should know how to do shear. At least check it. Just check it, right? To see if that hits the mark or not, right? Okay, so that is pretty much the basic stuff. All right, before we go on to the complicated one, meaning very sterile spacing, right? I want to show you something else. Okay, one thing we haven't talked about is that you see here. How do I determine VU max? Well, I don't know, Bob. You gave me a number. I work with that. In the exam, probably going to be the same thing, right? But in a job site, they will not be as kind as I am to give you a number. You have to figure out that yourself. So where can you get shear in the first place? There's something called diagram. Remember? Something called shear diagram. Remember? Something called freaking badass, right? Freaking bad body, freaking free body diagram, FBD, remember, right? We got to do the statics first, isn't it? We got to do that, right? So how do we do that? Well, I don't know, Bob. It's just straightforward. I don't know why you're asking this problem, because if I have a simply supported beam, right? And I can just get a shear, for example, if I have a distributed load, right? You know, let me save the effort, right? Just drawing it. I say a distributed load shear diagram looks like this. And I just need to pick out the maximum number, right? And we go with that, right? To pick this number and go with that, right? Are we happy? Oh, you're happy, right? Right? I would say, use, you boy have, right? Like Master Yoda, right? Too young, too naive, right? What really happening is that you cannot just use this number. So today, going to introduce you a new concept, right? So-called critical section for shear. Okay, and this is very important. I will have at least one problem in exam number 2, and the drawing problem, ask you to draw where the critical section is at, okay? I can now be more explicit than that, okay? So need to understand. So the reason for it is, if you take a look at ACI, and ACI in the section of 4.4.3.2, it says that I just want to make your life troublesome. I don't want you to have an easy life, all right, cannot just draw a shear diagram, find the maximum force, cannot do that. Matter of fact, here are the list of conditions you have to follow. First is called distributed loading. Okay, it means that, right, when I about to pick the shear, I need to take a look at the details. So if I draw my beam and nicely at the end of it sits like here, because that's where most likely my maximum shear force is going to be at, and I'm going to draw my nice neoprene pad right afterwards, right underneath it, and I say the support's going to be something like this, and you might even see some steel reinforced support, you know, just some rib plates here as a welded T-shape, and then have a nice neoprene pads underneath it to reduce the stress, nice cushion. And then finally, I have a column that's sitting underneath it, right? I have a column sitting underneath it. Okay, and in this case, right? In this case, the shear diagram, right? This is more like a blow up drawing, right? This is like a zoom in drawing of a end of this support right here. And this is distributed load, okay? Uniformly distributed load. Well, not uniform, but distributed load, okay? So this is what this one looks like, okay? Zoom in version, right? And ACI said, look, since I have a 45-degree angle of crack, and matter of fact, I know that I have two sections going to be critical, okay? Two sections going to be critical. What are those two sections? I say that if this is the center line of my support, okay, and translate into my shear diagram, right? Translate in terms of my shear diagram. This is where exactly my maximum shear force is at. Remember this fellow here, support here? And when I draw this diagram, right? Draw this diagram. This is actually the VU max. Okay, this is actually VU max right at the center line of the support. But ACI says you need to pick the shear right here, line up with the edge of the support. And I call this critical section CS1. That means I need to pick up this number instead to design. And this is CS1. Okay. That's the first critical section. I need to find out the shear force there. Okay, if it's distributed load. So happen that I have a linear distributed shear diagram. I'm happy, right? This one is bigger, but some cases it's not always bigger, right? Not always bigger. And then not only that, because I will have a 45-degree angle of a crack, and that usually start from here and cracked all the way through, and maybe stop right here, and there's a 45 degrees angle, right? But nevertheless, right, ACI says, I don't care, somewhere about a D, depth D, distance away from the edge of the support, you gave me another critical section that's called CS2. So that means, and this is, you know, scales, right? So that means somewhere here, I need to compare these two numbers, VU design, CS2. Whichever is bigger, dominance. Okay, whichever bigger dominance. Why, Bob? Why complicated? Because ACI says so. Because hundreds of people, right? White hair, no hair, right? And they discuss and they decided by experiences. Because what's really happening, you think of it, is that I may have localized stress due to the bearing, right? This is most likely I'm going to see a lot of shear puncture here. And then that high stress will tend to crack and follow this diagonal 45-degree crack. And then I have this right here. I only have about this high piece of connected piece, and that is the only residual compressive zone left, right? So that is the critical section. Okay, so there are two critical sections for this scenario and A. Okay, you think this is over, right? This is like John Wick #1, right? Chapter 2. I have joint. Okay, again, this is under distributed load. Okay, distributed load, right? And this is beam, column, joint. Beam, column, joint. So now, if I have a column, looks like this, and just cut from the top, and I have a beam like this, joint right here, And mind you that, right? When I say distributed load, I mean, I have loading on the shoulder of the beam, okay? These are my distributed load. Okay, and now if I draw the shear diagram, right? I want to find out the location of the critical section and find out the shear stress, right? And now remember I said Ottoman, right? Japanese animation, this one, remember this? I said always like this, not like this, remember? Well, I lied, right? I lied, right? Just this case, I lied. Why is that? Why is that? Why am I lying, right? Why did I lie? Because, right, this is at a continuous support, right? Continuous support, right? The shear failure is a bit different. Why is that? It is kind of like this, isn't it? Kind of like this, isn't it? Yes, indeed. The crack on right-hand side goes like this, 45 degree, right? But it is symmetric. Goes this one as well. So just in this case, it's an exception. Okay. So now we do not have to worry about this cut anymore. Okay. Don't worry about this cut anymore. Okay. I put a cross mark so you know this is not it. Okay. The only critical section is going to be distance d away from the edge of the support. That's it. So CS critical section here, critical section here. Okay. And literally every year I have identical problem just like this design. And guess what? Every year you guys make mistake, okay? I see all kind of weird stuff now. I even see something like this. I don't even know what's going on, okay? So remember this figure, okay? Cannot be simpler than that, all right? So B is distributed load, beam column joint, okay? Beam column joint. All right, C is a little bit different, right? But C is kind of extension of that. So C is a continuous section. Continuous section of beam column joint. Okay. It's basically same, but instead of one, I have a lot of end joint. So I have this kind of scenario, right? And this is no different. So the critical section is going to be distance d away, sorry, color. Distance d away from here, d away from here, d away from here, d away from here. And if you don't know how to draw it, right, I can show you, right? So the crack goes from here to here, here to here, here to here, and here to here, always from a lower end to the top, okay? Lower end to the top, and oh, my bad. And this is critical section, distance d away, critical section, distance d away, same thing here, same thing here. Okay, and that is not too bad. Now, when we are just about done, he says, wait a minute, there's an interesting case, it's called edge load. Okay. And from a glance, it looks just like a beam end, right? Beam end sitting on top of the column as we show in the case A, right? And when you are going to say that I have critical sections, right? Here and here, okay? And now don't, well, let me see here first. Okay, don't worry about it, right? It's gonna be the same, but now this is 45 degree angles, okay? And this cut right here, if I do a cut like this, okay? There's a lip for the section. And my distributed load is no longer on the top, but right here instead, okay? So critical section here, critical section here. Okay. And let me just finish this, right? And I will also have 3 other cases, right? One is D, and this is D1, I think. D2, I have a hanging over beam, just like this, okay? And now on top of the distributed load, I have And we know how to handle that, right? That is distance away, D from the edge of it, and call it critical section. But instead, on top of that, if I ever have concentrated load, right? So let me just draw right here, okay? If I have a concentrated load, okay, force here, I need to add one right here on the spot. Okay, so 2 critical sections. All right. Now, have you guys seen the balcony? Nice European structures or Paris, you know, near Eiffel Tower, you know, they have a lot of old buildings, right? Even in New Orleans, right? They have that too, right? French Quarter, whatever, right? And you have seen those balconies, right? And for the balcony, I have this beam as well. And normally I have a distributed load here. And this beam is sustaining a tension force. So I also need to check my shear here. CS. Okay. And last but not least is what we call the Gooder beam and Gooder joint. Okay. So in the plain language, it is just a big beam here. Okay. Try to draw my 3D drawing here. And then a joint by a small beam right here. Okay. And that's my cut. So instead of all those, well, besides all those conditions, okay, and this blue shaded cut is the critical section here. Okay, critical section right here. Okay, I think I got it. Okay, and this is my beam, and this is my Gooder, right? Okay, and that is my. So that is my critical section, okay? That is my critical section. All right, so you have seen so many of them, right? In exam, let me tell you right now, okay? In exam, you see this. For sure. You see this, for sure. And you will see this one here, for sure, okay? And here. Only 4 cases I will test you guys. The rest, you know where they are and they probably don't care so much. Okay, all right. And now that's how we're gonna do the shear design. All right, and why these are so important. This is why. Okay, one more thing, and it won't be long. Okay, let me just show you why we need design. And this is pretty much for next Monday. Okay, design for varying spacing S. Okay, design for varying spacing S. So what really happening is that we now know there are so many critical sections. If I draw a shear diagram of a uniformly distributed loaded and simply supported beam, and I know that my shear diagram looks like this. Okay, and I'm going to design a section for it. Okay, here is my dilemma, right? Oh, well, you know, I know there are 2 sections need to be checked. One is near the edge, the other is, you know, at a distance D away. And let's just say I'm going to use distance D away to save all my effort, right? So this is VU max, fine, but this is VU design, okay? I just won't be lazy, right? And I zoom in this fellow right here and I look at the triangle, right? Look at the triangle, I say, Bob, all am I doing is I just need to design a shear, okay? And for this value here, that is VU design load, okay? And I use this shear force to determine my stirrups spacing, right? So let me ask you a dumb question from me, right? If I have a given shear force, 1 shear force value, okay? How many spacing I can come up with? 1 shear force, how many spacing I can come out with? Come on, it's not a trick question. It's a dumb question. How many? 1, right? I can only get 1, right? What does it mean? It means that if I come up with a spacing of number 4, maybe 4, 9, 6 inches, right? means that I'm going to have 6 inches of stirrups spacing all across. Isn't it? And everywhere along the section, I basically says I'm going to have a shear resistance of VU design across this half span of the beam, isn't it? Right? If you present this design to me, I'll say, good job, 90 points. A, graduate, go to the job site. Okay, which is not the case, but I'm just exaggerating, right? And then if you take this design to your boss, he's gonna say, who taught you the concrete design? Right? You say, Bob, they're gonna call me and I might lose my job. Why is that? Because he will tell you, you young, foolish engineer, look, this is what we need and we get paid for, right? And yet you gave me this. That means all this are what? Extra. Is that right? Extra cost in stirrups, right? Extra cost in concrete, extra in everything. And in civil engineer, extra in safety is good. Extra in cost is not good, isn't it? So what you're gonna do? You say, well, can I do a spacing maybe in such a fashion that I can just do a nice spacing, right? Barely cover the line, isn't it? That's the optimal solution, right? But is there a continuous spacing? A definition of continuous spacing? Probably not, isn't it? You can have a 6-inch spacing here, 4-inch spacing here, but you need some distance, right? So in reality, you cannot do that. But instead, can we do this? All right, I can do that, right? I can do small triangles. It's not the best, but surely a whole lot easier than this fellow here. Much, much economical than the big giant triangle there, isn't it? So that means if I have a 6-inch spacing here, right? I have to reduce my spacing, right? To reduce my strength, right? A little bit. So maybe I can do 6 here. I can do 4 here. And I can do maybe 2 here. Oh, I don't even do anything here. Maybe just let the concrete take care of it, but provide some AV min. Remember, I need to provide some AV min. I'm fine, isn't it? All right, I can cover it. So this design strategy is called what? Various or varying spacing. Yes.
Wouldn't the spacing increase because you're decreasing your shear?
Oh, yeah, you're right. Man, thank you so much. I forgot. So 12, 24, 48. Oh, sorry. 12, 24, nothing. Okay. Varying spacing. Okay. So what does it translate, right? It translates into a visual image when the guy up there in the job site trying to tie up the cages, right? What the guy will see is this. Now, this is the top bar. And by the way, does the top bar take care of compression or tension? Well, you learned this part, right? Do I hear tension? Compression or tension? Compression, usually, okay? In a simply supported case, compression, okay? If you guys lost their confidence, tension, no. Here, tension, right? But I see reinforcement, right? In terms of cages. Now, I'm only talking about half span. So what really translate here is that I may have 6 inches here in this zone, and I start to have more spacing. And start to have more spacing. And I stop cold turkey from here, no spacing. And maybe provide 1 bar just to avoid that 24-inch of a dead zone. That's it. So that is very economical, right? And then you present this design to your employer, and please tell them you take class from me, right? And you say, oh, I took Bob. Who's Bob? Chenglin Bob. Oh, okay. Right? Do that. All right. So this is what we're going to talk about next class. Okay. I'll post the homework, but again, homework is going to be on section, so don't worry about it. Okay, not a whole lot. Okay. Thank you, and see you on Monday. Start recording.